Hello, and thank you for joining us for today's webinar, 3D Printed Rapid Tools for Injection Molding. My name is Kim Kaloran, and I'll be your host for today's event. Before we get into today's topic, I wanted to give you a brief overview of Stratasys. For those of you who aren't familiar with our company, Stratasys manufactures 3D printing equipment and materials that create physical objects directly from digital data. Its systems range from affordable desktop 3D printers to larger and more advanced 3D production systems. We are passionate believers in the value and power of 3D printing and in the change it can bring to the world. All Stratasys 3D printers build parts layer by layer. PolyJet technology, known for its smooth, detailed surfaces and ability to combine multiple materials in one part, employs an inkjet-style method to build parts from liquid photopolymers in fine droplets, immediately cured then with a UV light. We also have FDM technology, which is fused deposition modeling. It's known for its reliability and durable parts. And what it does is it extrudes fine lines of molten thermoplastic, which then solidify as they're deposited. The Stratasys portfolio of specially engineered 3D printing materials is the most comprehensive in the industry. It includes nearly 150 PolyJet photopolymers and FDM thermoplastics. So now on to the meat of today's event. I'd like to welcome our presenters, Nadav Sella, Solutions Sales Manager and Global Field Operations for Stratasys. And Nadav has been working in Stratasys for 6 years. He started as an application engineer at Object, then managed the pre-sales and applications for the emerging markets, including Latin America, and he is currently managing the solution sales worldwide for the tooling market. He started working on developing the market for printed tools for injection molding over 4 years ago while still at Object. And prior to that, he worked 5 years in the semiconductors industry as a project manager. He has a Bachelor of Science in Mechanical Engineering from Tel Aviv University and an MBA from Bar Ilan University. So Nadav, at this point, I will let you take it from here.
Thank you, Kim. Okay, so hello everybody. Today I'll try to give you a brief overview on our very exciting application of printing molds for injection molding. We call it PIMPT, just for shortening the long phrase. So we're going to talk a little bit about what is it good for using printed injection molding tools, where does it fit, giving flexibility in the prototype manufacturing, which is, I think, the main advantage of this application. We'll show you some sample parts and the benefits from these sample parts in terms of saving time and money, and showing you some tips and tricks to do successful molding with printed injection molds. After that, at the end, we'll have some questions and hopefully some answers for you. So, printed injection molding tools, what is it good for? So usually, as Kim said, I came from starting as an application engineer, doing a lot of benchmarks for prospects and customers. So in this slide, you can see a diagram of the product design life cycle, where everything starts with the CAD design, where you get your ideas. Usually you do some iterations in the CAD and look how the model or how your part looks and functions. Then companies go and manufacture usually what we call prototype 1, which is a more concept prototype used for visual appreciation of your design, just to get a feel on how the product looks like. And usually this prototype is manufactured using rapid prototyping machines. Usually the surface finish is important here, mainly the visual appreciation. After a few iterations of prototype 1, where companies can go back to the CAD and change some things, further down the road, companies need usually to create what we call prototype 2, which is a functional prototype, most likely manufactured from the real end product material and is designed to get the company the ability to do the full range tests on the part before starting production or before investing a lot of time and money in manufacturing steel or aluminum tools. So basically, what we say is that the rapid molds solution comes here in manufacturing prototype number 2, which is the functional prototype from the real end product material. So I would like you to watch this video from one of our customers in Europe. And here you can see actually a propeller, a cooling propeller for an electric engine. And here we can see the mold printed on our Connex machine. This mold is printed in 22 hours and costs less than $1,000. You can see the mold is, after the printing, is taken out of the printer and mounted on a standard 70-ton Arburg injection molding machine. You can see that the part is actually injected into the mold, and the mold is mounted on the machine, and the injection is done through a standard metal bushing that runs through a back plate here. The mold is being removed after the injection, and the part is taken out from the mold. So basically you get a fully functional POM, acetal, or Delrin, as usually it's called in the US. You get a time saving of between 700 and 1800% and cost saving between 40 to 80% versus aluminum or steel. Now this part was done for the functional tests at the end of the product design life cycle, at the point where, as I mentioned before, prototype number 2 was needed to do all the functional tests with a very high velocity spinning of that propeller to make sure that the design met the requirements that were asked by the customer, meaning reduced noise and increased cooling efficiency. So once we got to this point, where hopefully everybody understands what we're talking about here, meaning printing molds and injecting real thermoplastics in the mold, probably one of the questions that you all ask yourself is, where does it fit? Can I do any material? Can I inject any material into the mold? How many parts can I get out of the mold? What is the accuracy? All these questions we'll try to answer in the following slides. So the best fit for this solution will be thermoplastics with molding temperatures of up to 300 degrees Celsius, which is 570 degrees Fahrenheit, a good flowability, and candidates like plastics that you probably all know, like polyethylene, polypropylene, polystyrene, ABS, TPEs, polyamide, POM, which is Delrin, the example we just saw, and PCABS, and also some glass-filled resins like polypropylene with glass reinforced or nylon with glass reinforced. In terms of the quantities here, we're talking about low quantities that we get out of the mold, and this is again just to get you your first prototypes from the real end product material that you can use for your functional testing of your product, of your parts. So we're talking about between 5 to 100 parts, and again, it depends on the complexity of the part and the material you're going to inject. Of course, if you're injecting very high melting point materials like glass-filled nylons, or you are injecting a good flowability and low melting point plastics like polypropylene, the amount of parts that you can get out of the mold will be different. We're talking about here on mid-sized parts, less than 165 cubic centimeters or less than 10 cubic inches. And the machine type that you can use here, you can use from a bench plastic injection molding machine, like the one probably some of you saw in school, engineering school or plastic engineering school, up to machines of 50 to 100 ton standard molding machines from any manufacturer that you are working with. Here you can see on the right some examples of injected parts. The upper example was done by one of our customers, Nitro Healthcare, in Northern Ireland. They did a project for 3 months evaluating this process, and they own a Connex machine as well. You can read about it in the white paper we published in the website if you'd like further. And you can see on the bottom right, you can see a mold from one of our customers in Germany, an automotive part manufacturer. It's a very, very complex mold that was done to reduce time and cost to get the first functional parts to testing. And we have a movie about that as well that you can watch on YouTube if you like. Now, when we're talking about printed injection molding tools, as I said, we're talking about flexibility in the prototype manufacturing. So basically, it all comes down to the prototyping manager or the R&D manager to make a decision on how to produce a part at a certain point in time in different projects. So there are a few routes that you can take, and I will elaborate a little bit further down the presentation, the next slides. But basically, you can see a kind of a decision here made to choose between rapid molds, which are fast, cheap, and can get you a low volume of parts, between CNC, which is slower to manufacture, more expensive, but will give you a large volume of parts. So this is one of the decision points where you would need to weigh in all the factors, meaning how many parts you need for the process. Is the surface finish very important or not so important? And by making the right decisions, you can save time and money and give your company flexibility in your prototype manufacturing from the real end product material. Let's review the last, let's say the last comment in the next 3 slides. So what you can see here is a graph that incorporates all the players that can help a company create prototypes from the real end product material. So representing the, let's say, the additive manufacturing world is the FDM here. You have a plastic part fabrication, which is a direct milling of parts from a plastic block by CNC. You have prototype injection molding, which is milling an aluminum mold and then injecting the parts in the mold. You have surplus injection molding, which is taking or buying an existing mold and modifying it to accommodate your new part. And we have conventional injection molding, which is milling a mold from steel using CNC, EDM, or other possibilities. Basically, it will be probably CNC and EDM. So what you see here now in the golden rectangle is placing the printed injection molded solution in the realm of all the other players in the market and showing you where does this solution fit in terms of the X and Y axis here in this table. So on the X-axis, you have the initial cost of the method that you see in the graph. And on the Y-axis, you have the marginal cost of creating or producing another part. So as you can see, quite obviously, conventional injection molding will have a very high initial cost, but the marginal cost will be very, very low in terms of how much it will cost to produce the 3rd prototype, the 4th prototype or part, and the 5th, and so on. So once you get the injection mold or you milled it from steel, it will cost a lot of money, but the cost of creating additional parts would be very, very low. On the other hand, you have the FDM, which has a very high marginal cost, but a very low initial cost. So in the golden rectangle, you can see where the printed injection molds come. They have an initial cost much less than conventional injection molding, surplus injection molding, and sometimes plastic part fabrication and prototype injection molding. And they have a marginal cost which is less than directly printing a part from STM or any other additive manufacturing method. And of course, you get the final part from the real end product material in the end process that you're going to use to manufacture your end product, which will probably be injection molding. Just to note that this data was taken from a study done by Toyota and Yuma Snow some many years ago, and what I did here is just put an overlay on this graph to show you how the printed injection molding tools come in hand with the other solutions in the market. In this slide, you can see two different axes to show the same issue here, or the same problem that everyone faces when deciding how to produce a part. So here you have on the x-axis the initial tooling time, and on the y-axis the marginal production time. So the initial tooling time, as you can see, will be much lower than conventional injection molding and prototype injection molding and surplus. And the marginal production time will be lower with printed injection molds than plastic part fabrication and FDM. In the last slide from this study, you can see how the printed injection molding tools come relative to the number of parts that you can obtain from a mold and the part complexity. So as you can see, of course, very, very complex parts with a lot of moving parts in the mold, of course, cannot be manufactured, but relatively complex parts with low quantities can be manufactured with the printed injection molding tools with a lower cost and a lower time. Here you can see in a maybe more clear graphical way, you can see where the solution comes relative to other solutions to produce molds that are available in the market. So you can see steel and aluminum tools, direct metal sintering tools, cast resin tools, usually epoxy, and here you can see the polyjet tools in terms of how many parts you can get relative to the material you are going to inject into the mold. In terms of the material that you are going to inject in the mold, we divided the plastic world into 4 groups from A to D, where A is the most easy plastics to inject, and D will be the most difficult plastics to inject in terms of melting point, viscosity, and other parameters. So you can see that in group A, materials like polyethylene, polypropylene, polystyrene, ABS, and the whole TPE family, which is a very important group here, are very easy to inject, and you can expect to obtain relative large number of parts from a single printed mold. Just as an example, the TPE family is a family that is very hard to simulate when using additive manufacturing, and in my let's say in my experience as an application engineer, most of the companies find it very difficult to simulate TPEs and get them as functional prototypes to run a functional test if it's in the automotive industry, for example, under the hood applications, high temperatures, and so on. So here actually you can get TPEs part from the real end product material very quick. Group number B, like polypropylene with glass fibers, nylon, POM, and PCABS, which is, again, just a few examples of this group. And also group C is possible using reinforced nylon or polycarbonate parts, we can do as well. But as I said before, you can see that the number of parts that you can expect to obtain from a mold decreases when you get to the higher or tougher materials to inject in those groups, as we showed. I would like to show you some examples of parts that were injected to give you some, let's say, some live images of the things that we just discussed. So here you can see a 3-part mold of a part taken out of a pump. You can see parts molded to the same mold from acetal, from reinforced polypropylene with 20% glass fibers, EPDM, and also some nylon 6/6 with 20% glass reinforced. In this slide, you can see the molding temperature for each one of the materials that you saw in the last slide. This can be used as a reference for you if you would like to try it, or just compare it to the molding parameters that you know from each material. And here you can see an example in the picture of where this part came from in terms of which product. This part is, again, as I said, is quite a difficult part because of the thickness of the plastic, and also because there is an undercut with the threads of this cork. In this example, you can see a relatively easy part. This is an ice cream spoon. This is actually a production mold that was printed from the digital ABS material on our Connex machine. You can see 2 different examples here of mounting the mold on the injection molding machine. Again, this is here again, it's an Arbog machine, standard 70-ton machine. In this part, you can see that we managed to, you can get a relatively high number of parts from the mold because the mold is quite, the material here is polypropylene. It's quite easy to inject, and we were very easily, we got around 600 parts from the mold with no any visible degradation of the mold. You can see the time saving and cost saving here, which is substantial. Time saving here was 3,000%, and the cost saving here was 44% over aluminum and 75% over steel. The numbers here were taken from 2 different tool makers that we asked to get the price proposal and, of course, the lead time. And this was done, this specific project was done in Brazil, so the price offers and time, also the lead time, was taken from 2 different Brazilian tool makers. The next example is from one of our customers in Europe, an automotive parts manufacturer named Seufer. Again, you saw this part in the last slides, a few slides ago, and you can watch a video, a customer testimonial video from this customer as well in YouTube. As you can see, this part is very, very complex, and when you will watch the video, you will see that a conventional production mold of this part cost about 40,000 euros, which is probably about $55,000. And the mold that they printed here was printed in one day, and the injection was done on the day after. So they actually could get the functional part in their hands the day after they started printing. This part was injected in few materials. We injected it from high-density polyethylene. We injected it from polypropylene, and as well from reinforced nylon. This is another example here, parts from ABS, injected in ABS. This is from one of our customers in the UK. You can see again the injection parameters here, the nozzle temperature, injection pressure, holding pressure, and other parameters. This part was challenging because of the deep bosses that you can see here. And you can see, for example, in the red part, you can see that the boss is closed, And on the black part, you can see that the boss is fully open and correct. The reason is that they use the metal insert to create those very thin, long bosses incorporated in the printed tool. Another interesting point here on this part is that after they injected this part, they saw that they have a venting problem in the tool design, and some of the ribs here were not full. And this actually showed them that when they come to manufacture the end product tool, they will need to add the sufficient venting to make those ribs fully functional. This is again another advantage of using the printed tools to catch design errors before the real end product molds production starts. The next example here is the test parts that we have done in order to make sure that we are on spec in terms of the dimensional properties of the part after injection. We've done a lot of tests on this part and measured different points after 20, 50, and 100 shots to the mold. You have some very typical features in injection molding. In this part, you have boss with ribs and without ribs. You have a snap fit here, and you have a very common living hinge here that is very, very hard to simulate in additive manufacturing. And here, of course, the molded material is polypropylene that is perfect for living hinges. So again, to create a functional part with living hinge, it's much, much easier to use the end product material like polypropylene and inject it into a printed mold in one day. In terms of the dimensional properties here, so we found that we are in spec in terms of the industry standards. The deviation is between 0.1 and 0.2 millimeters, which should be about 0.003 of an inch, between 0.003 of an inch to 0.006 of an inch. In the next example, you can see the propeller that we saw before in the video. This is from a case study we have with one of our customers in Europe, Budapest University. You can read all about it in the website. Basically, you can see also the time saving and cost saving for this project, which was between 700 and 1800% in terms of time, and between 43 to 72% in terms of cost versus aluminum and steel. This is a POM part, by the way. This is the injection parameters of the POM part. In the next example, this is one example of TPE materials injected into a printed mold. And you can see the quote from our customer saying that compared to silicone molding, 50% in time and cost are saved, as well as the real material prototype made. This is parts for the automotive industry. And again, as I said before, TPEs or rubber-like parts are very hard to simulate. Either using silicone molding and then you get the parts from polyurethane, but it takes time, it takes money, and at the end you don't get the real part in your hand or the real material in your hand. So here, again, it's a very, very big advantage. Now, after seeing the examples, I would like to talk a little bit about some tips and tricks on how actually to perform injection into printed tools. So it all starts with the mold design, and again, we have a very detailed white paper in terms of all the tips and tricks and showing customers what to change in the mold design and in the process to make a successful injection. So I would like to go through a few tips and tricks here, and let's start with the mold design or the tool design. So in terms of the gate, basically what we would like is to reduce as much as possible the temperature and the pressure going into the printed tool. So we would like to use a screw gate or an edge gate when we design a tool to be used with our Connex machine or printed in 3D. We would like to increase the gate size over traditional gate sizes to minimize the stress here. So we don't recommend tunnel gate, cashew gate, banana gate, and point gate. So try to stay with the screw gate or edge gate. In terms of draft angle and shutoffs, so to facilitate the injection of the part from the mold, we would recommend to increase the draft angle when possible, or if possible, up to a maximum of 5 degrees. And to inset the shutoff faces, due to the printer tolerance, which is 0.1 millimeter or a little bit better than that with the small parts, to make sure that you have a good fit in the shutoff faces. So insert the shutoff faces about 0.05 to 0.1 millimeter before you print the mold. Here you can see some pictures on where exactly do I mean to inset the shutoff faces. Regarding the mold components, so for the ejection system, we recommend to undersize the ejection holes. The ejection holes, of course, can be designed, of course, with the mold design like you do in a regular steel mold, but undersize them by 0.2 or 0.3 millimeters, and after the printing, rim them to get a perfect fit. The cooling cycle, if used, locate it about 8 to 10 millimeters below the cavity surface. So if you are going to use cooling channels, and again, one point to mention here is that cooling channels work with the printing tools, but are, of course, much less efficient in cooling the mold, cooling a plastic mold, in this case a thermoset mold, than cooling a steel mold. So in terms of your expectations, do not expect that it will have the same cooling effect as you would have in a steel mold, but our experiments show that it helps, but it doesn't have a very big effect. So if you use it, locate the cooling channels about 8 to 10 millimeters below the cavity surface. Here you can see some examples in the bottom right of the mold you saw before with cooling channels incorporated. It says here that it's not recommended, and again, this is because the heat flow ratio here, or the heat flow rate here, is not as high as with the steel tools. Here you can see a picture of the mold design showing the red holes for the ejection pins, and the green holes for the holes to mount the mold on the injection molding machine. The mold fitting and finishing. So you can see here what we mentioned before, to rim the ejection system holes. Okay, in terms of the mold base option, you want to make sure that the mold sticks out about 0.2 millimeters or 0.008 of an inch beyond the mold base. This is to make sure that when you clamp the mold, you will have a tight clamping between the two mold halves. You can see on the bottom right the ejection system fit. after the rimming. In terms of the finishing, the surface finishing, so you can see two examples here, one colored in red and one colored in green. So the red colored surface is the surface that you might want to finish in order to facilitate the ejection of the part from the mold after the injection. The green area is an area that you might want to finish just to make a better surface finish to your injected part. Both of them can be done with standard sandpaper, starting with a 180 to 220 grit, followed by up to 2,000 grit of sandpaper to finish the mold. The mounting option of the mold on the injection molding machine. So as we said before, you can mount the mold even on a bench press, and this option is not shown in the pictures here. But in terms of standard injection molding machine or industrial injection molding machine, so we have a few opportunities. You have the opportunity to put the mold in a mold base, which most of our customers are just creating a mold base with a standard size that usually they would use for their inserts, meaning that they think about the standard part size that they will usually use, and then create the mold base to accommodate the insert that then would be printed. The insert is the same size every time, and just the part is different in the insert. So this way you can switch between inserts very easily, and you have the mold base ready for use whenever you want to print an insert and use the printed tool. The second option here is to use a steel plate with ejection. In the last case of the mold base, again, the ejection system can and is used usually. So in the bottom you can see a steel plate with ejection system. And the third option can be just to mount it directly on the back plate like you saw in the movie with the propeller. Now, the advantage here is that it's the easiest, let's say, easiest and cheapest way to mount a mold on the injection molding machine. But the disadvantage is that you will need to remove the mold after you inject each shot to remove the part, to eject the part. The mold is glued with a two-side tape here on the back plate, and again, the molding itself is done through a standard metal bushing that runs through the back plate up to the mold. As you can see, the mold here is closed with a sellotape, and after the clamping position is set, the clamping force is applied and the part is injected. In terms of the process development, so we would recommend a conservative settings to maximize the tool life. Start with a very low pressure and temperature, do some test runs, inspect the results, and adjust as needed. In the picture here, you can see the test shots to dial in the parameters with the part that you saw from the sulfur case study. So the initial settings here is setting the injection molding time limit to 20 seconds, setting the pack and hold phase to 0 pressure and 0 seconds, of course at the process development stage, setting the shot size to 70% of the standard volume, and the barrel temperature at the low end of the resin recommendation. The injection speed should be at the low end of the resin recommendation, and 10 to 20% of the machine's maximum screw speed. The cooling cycle should be for small and thin parts about 40 seconds, and for larger parts or thicker features 90 seconds. Of course, you should inspect the parts after the first few shots, just according to your findings. Okay. Now, in terms of the trial shots, increase the shot size. Target is 90% of the part volume or the shot volume. Adjust the packing pressure to 30 to 50% of the injection pressure, and increase holding time until you get a perfect part. If you see some sink marks at the part, so adjust the barrel temperature, injection speed, and inspect the results again until you get a nice, smooth, and fully filled part. Do not overcool the part. It will cause the part to shrink and to grab the tool. Again, you can facilitate the injection, as we said before, by polishing the tool in the let's say in the problematic areas that you are afraid that the part can grab the tool and interfere with the ejection of the part. Regarding the cooling, so it's very important to cool the tool down between each shot, or basically making sure that the tool temperature will not rise over 50 degrees Celsius or 120 Fahrenheit. Our best practice is to cool the tool with compressed air. In this picture here on the right, you can see compressed air, a compressed air jig mounted on the injection molding machine, and set automatically to cool the tool down between each shots for a period of time, 20 seconds, 30 seconds, and then the next injection cycle takes place.
Great. Well, thank you very much, Nadav. Do you want to give a 30-second summary about the benefits of using this process for injection molding?
Yeah, thank you, Kim. So, yeah, basically I would like to summarize and say what I said at the beginning, so that I think that in a world that everyone is running and looking for new solutions to try and cut time and cut cost, I think this solution gives wonderful flexibility to manufacturers to use it whenever possible and to cut time and cut cost. So having let's say a injection part in 1 to 2 days if you have the machine in-house, and maybe in 1 week if you are using an external provider, gives you the possibility to move some of your projects into printed tools, and at the end cut your overall tooling cost and time, and make yourself available for other projects, or just cut your business costs and make it better at the end.